dead space.
Or dead air. Alright, so solve for K. Once you get the rate constant, the rate law, you can solve for the rate constant. The nice thing, this is just one example, but this applies to literally any example or problem that you could see. It's just the numbers are going to be different, the reaction will be different, but it's always going to be rate equals K times concentrations of reactants raised to whatever you figure out. So you can just apply this to future problems. Alright, so Trevor, what experiment did you use to solve for K?
I used experiment 1.
Experiment 1. So the rate for number 1 is 1.2 times 10 to the negative 3. Now, what is the unit on rate? I'm going to label the units of all my numbers so that we can figure it out.
Big N/S.
Right, so molarity per seconds equals K, and now I'm just going to divide these over. So it's going to be 0.1, and this is in molarity, times 0.01, and that's molarity. Right? Okay, so this divided by those two multiplied together. So let's just get the number. What'd you get, Trevor?
1.2 times 10 to the negative 4.
Try again. I just got 1.2. Who got 1.2? Yeah, some of you got 0.12, and so yeah, you just maybe forgot this. Did you not have 0.01 here, maybe?
I might not have.
Yeah. You guys can all do the math. So if you make a mistake, that's what it's just a silly mistake. You guys can all do that. So it's 1.2. Now let's look at the units. So I'm gonna get rid of the numbers. So we have molarity per seconds over molarity squared. Right? Molarity times molarity is molarity squared. So what cancels out?
Big N.
Can we write this a better way so we can see what cancels? No? Okay.
Separate the.
You want to separate the m's? So it's m over seconds.
Yeah, one of the M's can go out.
So this and this cancel out? Okay, so then what is that?
Molarity.
Well, this is per seconds, right? And then this is per molarity. So how would we write this as one unit? Because you can't do this. Right? That's crazy, right? That's crazy.
Second times N to the negative 1, whatever the thing is. Bring it up.
Bring it up, she says.
You know what we do when we.
That's the unit.
Yeah. See, it's the negative 1.
Or
Nobody listens.
it's 1.2 per molarity seconds, which looks weird. So on the AP test and book notes, you're going to see me write it this way. So 1 over seconds is the same thing as S minus 1. 1 over molarity is the same as M minus 1. So I'm gonna help you out right now. Okay. Sometimes this I can see, even for me, I gotta really kind of concentrate sometimes when I do this and figure out, okay, what's it look like rewritten. So it does help to memorize this, and I don't like saying that, but so let me lay it out for you. First order. So write this somewhere, maybe in the margins of your notes. First order. For first order, K is S minus 1. Second order, K is molarity minus 1, seconds minus 1. Third order, K is M minus 2, S minus 1. Zero order, K would be just molarity per seconds, because zero order is rate is equal to K. Because the concentration of A raised to the 0, that's irrelevant. So rate is equal to K, so those units are exactly the same. So for zero order, I guess I'll just write 0. Zero order, your units on K is the same as rate. First order, it's always, now I wrote S minus 1, you're going to see there's problems where instead of seconds, it's minutes. Or it could be days, it could be years. So really it's time to the minus 1. To be a generic kind of unit. It's always molarity, but it's time minus 1. So first order, this is a 1. Second order, these add up to 2. Third order, these add up to 3. So that, it would behoove you to memorize that. It just makes your life easier. If you can memorize it, and let's be honest, a lot of times in school, even in college, the more you can memorize, doesn't necessarily mean you've learned it, I get that. But it just makes problems like this a lot easier, because once you do the math, you just say, oh, it's second order, so 1, 1. And then you move on, instead of spending 5 minutes or whatever trying to figure out the units, right? So I think it's okay to try and memorize that, all right? But I always tell my students this, because I do that. Years ago, I just said, I'm going to memorize it, because even for me, sometimes I get confused or make a mistake. So hopefully that helps. All right, let's go back to the homework now. Let's go to 576. The rate law for that experiment, did anybody figure it out? And by the way, the answers are always at the back. After all the questions at the end of the chapter, they list the practice exercises like in order. So the answer, what is this, 13.3? K times S2O8 minus 2 to the first power, I minus to the first power. So it's second order. It's just like this experiment, except it's S2O8 minus 2 times I minus. So it's a second order reaction. But I'll go through it a little faster to make sure we got it. And then we will move on. And sometimes I like to refresh, why are we doing this? What is the point? If you can determine these concentrations and rates experimentally, then you can write what's called the rate law, and then from there you can figure out the graphs, and from there you can figure out unknowns, right? So you can apply it to that, like if you, or projections, right? So if you change the concentration, this is how long it should take, right? So that's kind of one of the reasons that this exists and it's a thing, is taking knowns and then figuring out unknowns or future scenarios. All right, so I'm going to take reaction 2 and 1, 2 divided by 1, to figure out the exponent on I minus. I'm going to take reactions 3 and 2 to figure out the exponent on the S2O8 minus 2. So if we take 2 divided by 1, it's going to be 1.1 times 10 to the negative 4. Wait a second. Nope. 1 divided by 2. Why do we want to do 1 divided by 2?
One's bigger.
Right, because 1's bigger. There you go. So we want 2.2 times 10 to the negative 4 divided by 1.1 times 10 to the negative 4 equals k divided by k. And then we got 0.08, 0.08, those cancel. My I is 0.034 and 0.017. So what's this divided by this? 2. This divided by this? 2. Sorry, this is going to be y and y, so y is equal to 1. All right, if we do, what are we doing now? Now we're doing 3 divided, I'm not going to write this out, sorry. You guys are smart enough, I think, and at this point you should be good. So if you look at experiment 3 and 2, you see S2O8 doubles, I minus stays the same, and the rate doubles. So if S2O8 minus 2 doubles and the rate doubles, it's a direct relationship, it's a 1-to-1, so the exponent is 1. So this is how you show it, but you can also kind of just look at it sometimes and figure it out. If the rate does the exact same thing as the concentration, it's a 1. If the concentration doubles but the rate quadruples, then the exponent's a 2. I'll show you one of those today. So, anyways, so the rate law is rate equals K times S2O8 minus 2 to the first, which you don't necessarily need to label, so you can just leave them like that. That's second order, each one's raised to the first. All right, and then how do you solve for the rate constant? If you take experiment number 1, it would be 2.2 times 10 to the negative 4 equals K, and this is divided by 0.08 to the first and 0.034 to the first. So you do all this business, and the rate constant is, who got it?
Point 0.8.
Yeah, but they got 8.1 times 10 to the negative 2. So 0.081 they got. 0.081, and that's molarity minus 1, seconds minus 1. Okay, go, well, hold on. Give me a second here. So, if we were to graph 1 over the concentration of one of these, all right, so this is like the generic graph here, this slope would give us the K, which would be 0.081. All right, this is, I'm going to talk about those equations in our reaction sheet today. All right, let's take a break. Then when we get back, we'll go over number 13, and then we're going to take more notes.